All right, guys, I hope you through this next handout. I'm going to do just a couple of random practice problems for you. So in this, we're going to be referring to both the Pythagorean Theorem and special right triangles to answer questions about right triangles. So here I see that I have a right triangle and I am missing a leg. And I've been given the hypotenuse and the other leg. So I'm going to say that a squared plus b squared equals c squared. That's my Pythagorean theorem. And then I'm going to go ahead and write in that 12 squared plus y squared equals 16 squared. Now, just for the record, I want to see this setup, right? The setup is critical, that I can see that you know how to set this up. Now, how much you want to show from here is up to you. I would at least say that y squared is equal to 112 if you want to skip a few things and do that on your calculator, and then show that y is approximately 10.6. And that's an acceptable number of steps and proof of your Pythagorean theorem work. Next problem we're going to work on is number 6. And I noticed that I have the hypotenuse missing here out of a 30, 60, 90 right triangle, and I've scribbled out the x, and I'm going to call that a. And why am I going to do that? Because I want to save the value of x for my model. So I got my 30, 60, 90 triangle. I just basically am taking this, right, and I'm superimposing it over this. So here's what I notice. I notice that I have the value of this leg. It's equal to 14. So all I really need to do to solve for all the other missing pieces is obtain the value for x. So I'm going to say x rad 3 equals 14, divide by rad 3, divide by rad 3. And I'm going to get that x is equal to 14 over rad 3. Now we can't leave rad 3 in the denominator, so we're going to rationalize that. We're going to get 14 rad 3 over 3. So that is the value of x. This hypotenuse is worth 2 of those. So a is worth this times 2. So that's going to be 28, which is 14 times 2, rad 3 over 3. Now that as a decimal is 16.16. So you could have turned the 14 point rad 3 into a decimal, which is approximately 18.08, and you double that and you get 16.16. So I'm going to say a is either approximately 16.16 or is exactly 28 rad 3 over 3. Either or, your choice. Now on number 8, I'm going to approach this using both Pythagorean theorem and special right triangles to make sure that we see that they are both useful. All right, so this is a 30, 60, 90 right triangle, and here's my 30, 60, 90 right triangle model. Now again, I would have this on an index card. I would have this as a traveling show, so it's always in front of me. I know that my hypotenuse is worth 2x. I know that the shortest side is opposite the smallest angle, which is x. I know that my middle length side is opposite my middle angle, 60 degrees, which is x rad 3. And I'm going to take this, I'm just going to superimpose it right over here. And so what do I know? I know that 4 is equal to 2x. So I say, well, I'll need to solve for x, and I'm pretty much home free. So 4 equals 2x, so x is equal to 2. Okay, so that makes b worth 2. How about a? A is going to be 2 rad 3, and we are done. But just for the record, if 4 is the hypotenuse, so 4 squared should be equal to b squared plus a squared. And we just said that b was worth 2. So 4 squared is equal to 2 squared plus a squared. That's 16 equals 4 plus a squared. So a squared is equal to 12, right? Or a itself is the square root of 12. Square root of 12 is 4 times 3, or 2 rad 3. So the Pythagorean theorem works. But of course, special right triangles worked way faster. So the point is, you got some options. Exercise your options. Work smart, not hard. Okay, so first off, on number 9, I noticed that I have a 45, 45, 90. And how do I know that this is a 45, 90? Because rad 2 is all the way around the sides, which tells me that my side lengths are the same, which means that this must be an isosceles right triangle or a 45, 45 right. And I know that my model states that the legs are worth x and the hypotenuse is worth x rad 2. And I'm looking for the value of z. Okay, no problem. So I just need to solve for x. I know that x is worth rad 2. All right, so this is also worth rad 2. Whoops. So what do? I say, well, hey, if x is worth rad 2, then x rad 2, right? X is worth rad 2, so that's rad 2 times rad 2, or rad 2 squared, which is rad 4, which is 2. So essentially, anytime you see a radical times itself, the number just falls out, i.e. 117 rad times 117, right? Square root of 117 times 117 is the square root of some big number, and the square root of that number is 117. Okay, I digress. So what we're saying here is that the value of the hypotenuse is worth 2. So z is equal to 2. But what about the Pythagorean theorem? Square root of 2 squared plus the square root of 2 squared is equal to z squared, because z is the hypotenuse, and these were the legs, right? So rad 2 squared, as we just said, would be 2, plus rad 2 squared would be 2 equals z squared. So that's 4 equals z squared, and the square root of z squared is z, and z is 2. Wow, blow me away. Z is still 2. Again, special right triangles or Pythagorean theorem, your choice. So we have, according to Sophie's handheld GPS, she's walked 3 miles north. Okay, so 3 miles north. Now for the directionally challenge, north, we'll say is quote-unquote up, although up technically is off the earth, east, south, and west here. Okay, so she's going to go north 3 miles. So here's her starting point, 3 miles north. Then she turns right and walks for 0.5 miles. And she goes east. Then she turns left and she goes 2 miles north. Then turns right and walks 1 mile east. And so on and so forth. So I guess what you're going to have here is a series of twists and turns. Okay? And I'm not saying this is what it looks like. All I'm saying is perhaps, you know, we go there. And of course, this is bogus. But you're going to have this moment where it says, how far is she from her starting point? So at some point, I think we're going to have to form a right triangle, right? So find a right triangle whose hypotenuse is the distance being asked for, right? We're drawing the picture as it happens. We should be able to take all of these Eastern moments, right? If you look back, and I apologize, I might have gotten a little overzealous with the blue there. If you look back, you'll see that she's just gone north and east and north and east and north and east and one south. And south would just be a correction or a subtraction from north. So at the end of the day, she's only gone this way and this way, this way and this way, and then there's going to be some sort of correction. So there's going to be this moment where really all you need to do is figure out the sum total of east and northern movement. That's going to be your eastern and northern moment, or I guess I should say eastern and northern distance traveled, and you're looking for that absolute distance. Number 13 asks you for the coordinates of point C over here. Now the first thing I see here is that we have this circle that's sitting on the coordinate grid system. So first I just wanted to double back to the definition of a circle, since we've never formally defined it. It's a round plane figure. And again, plane means that this is two-dimensional. Okay, so a circle is two-dimensional. So we have this plane figure, right? It's flat. And the boundary is the circumference, right? What's the circumference? The distance around the circle, sort of the perimeter, so to speak. But perimeter is reserved for polygons, and this is not a polygon. So it gets its own special term. The distance around is the circumference. So the circumference is the circle, right? These points that make up the circumference, they are all equidistant from where? From the center, right? So what makes a circle is that it's this collection of points all the way around this thing, right? There's an infinite connection of points on a plane, right? So all these points are coplanar. They share the same plane, and they are all equidistant to that center, which brings us to the next piece. The radius. What is the radius? A straight line from the center to the circumference, right? So the fact that they are all equidistant, what do we call that distance? We call that distance the radius. So what's the radius of this circle? Take a look at these coordinates, right? Think about that. That's the distance from here to here, the distance from here to here, and the distance from here to here, or here to here, or here to here. They all share the same distance. Now, taking that into consideration, notice I've created a nice little right triangle. And if this is 150 degrees, then this angle right here should be 30 degrees because this is a straight line, or I should say line. All lines are straight inherently by definition. So that's 30 degrees inside right here, this little angle right here. So if that's the case, and this distance is known, right? That's my radius, and at this point you should know what that value is. Then I have a special right triangle, folks. I have a 30-60 right triangle, and I should be able to ascertain the location of said coordinate. And you're asking, well, how? All right, so I'm going to draw this thing here. So here, I know this is 0, 0, right? Because that's this moment over here. Right? This and this are the same spot. So that's 0, 0. Okay. Well, once I go this way, so many coordinates, knowing that this value is 8, oops, I just gave away the farm. Since I know that's 8, and this is a 30, 60, 90 right triangle, I know that this is x, I know that this is 2x, and I know that this is x rad 3. The distance to the left must be the x coordinate. And the height of that must be my y coordinate. So I can figure out, I can ascertain what that xy coordinate is just by using some special right triangles. And then I can take these coordinates and apply the distance formula and double check that truly I do have the correct set of values, right? It should come out to be the length that I already knew this to be. Or wait, even better. I could just perform the Pythagorean Theorem with this answer, and I should get the length of this side. Why does that work? Because the distance formula is the Pythagorean Theorem in coordinate geometry form. So this is a lot of stuff from throughout the year now is sort of crashing together, and it should be fairly interesting. Next, we have quite an interesting problem. Okay, so it says, give the length of the longest diagonal of a box whose dimensions are 4 by 6 by 10 feet. Okay, so these are all in feet. So this is feet, feet, feet. All right, now this comes from the back top right point to the front left bottom point. This thing is traveling through the inside of the box. So there is this hypothetical right triangle going through the inside of the box. Now, I know that this is 10, but I don't know this point. I guess I'm going to have to figure that out somehow. It's a box, so this is inherently a right angle. I could figure this out. I could use that and my 10 to figure this out. This, my friends, would be the final answer that we're looking for. And on this last piece, acute, right, or obtuse, this is all from some former notes in homework number 1, right? The Pythag and converse, right? Go there for the notes and support your answers with work, right? So you need to support your answers. I don't know, but for me, anybody just writing words here, so you got a 33 1/3% chance of getting it right. I want to see some work to support that. Good luck.